Okay. Hello, everyone. I'm gonna kind of build on Carolee's talk about surface elevation tables, and here I'm going to focus in particular on data analysis. So, to start off, this presentation will kind of rely pretty heavily on work by one of my former and one of my present students. So, to kind of introduce them first, on the left is Krista Jankowski, whose work we'll start off with, and on the right, Kwandong Lee, who is currently doing a lot of SET work. So let's, before we go there, put this all in a little bit of historical perspective. And if there's one name that a lot of people would probably think of first when they think of SETs, it's the name of Don Cahoon at the U.S. Geological Survey, who has published extensively on this method. And this is one of his earlier papers from 95, where perhaps for the first time, he and his colleagues combined SETs with marker horizons. And that basically allowed them to separate between surface elevation change and vertical accretion, and as a result, to infer the rate of shallow subsidence. That, of course, was a pretty significant step forward in allowing us to get a better understanding of coastal wetland processes. So this is a more recent overview by Don Cahoon from 2015 that shows, what I would say is still probably fairly state-of-the-art methodology that is used in these studies. And one thing that is very commonly done is the SET system that is sitting here in this marsh is often linked to records from tide gauges. And basically, the idea is that we look at a nearby tide gauge to compare the rate of relative sea level rise in that particular coastal zone, and then compare that with the rate of elevation change at a marsh location to basically determine whether that wetland is keeping up with relative sea level rise or not. One thing we'll see is that even though this has been very useful, there are some pretty significant limitations to this approach, and we're now at a point where we can potentially really advance to something that is more sophisticated and more data rich. So speaking of data rich, my presentation will rely entirely on examples from coastal Louisiana, which is kind of a blessed coastal region in the sense that we have an overwhelming amount of data through this system known as the Coastal Reference Monitoring System, or CRIMS. This is a map that shows about 400 monitoring sites where, in fact, a lot of environmental parameters are tracked over time. At least 300 of these sites have an SET marker horizon system, and that's, of course, what we will be focusing on here. If you're interested, here is the link to the CRIM system. One of the really nice things is that all the data are publicly available for anyone to download and to play around with. And it's a really tremendous resource. In the interest of time, I'm not going to take you there, but I would encourage anyone who's interested to go and have a look. So back to that SET tide gauge comparison. If we look at tide gauges from the permanent surface of mean sea level that are available from the same region, we immediately see that there's actually very few of them. And in fact, what's shown here on this map, not all of them are even operational anymore. So this is really one of the problems, that in many cases, these SET measurements are compared to very sparse tide gauge records from a given region. So that's one of the issues we have been working on to try to get away from. And that kind of takes us to this study by Krista Jankowski that I will start off with that we did a number of years ago. This is a cartoon that is basically an adaptation of earlier cartoons that you may be familiar with. This is from the Webb et al. Overview in Nature Climate Change. And basically what Krista did was she obviously used the SET system with the marker horizon data that is shown here in the middle, and then linked that to GPS data that give us the deep subsidence component. The surface elevation table marker horizon combo gives us the shallow subsidence component. And then, of course, we need to have information on sea level rise. In this case, we're going to start moving towards using data that are independent of tide gauges. And I'll get into that in more detail in a moment. So the approach that she used is a little bit different from that surface elevation change tide gauge comparison approach. In this case, we are using the combination of GPS and SETs to calculate the total amount of subsidence, so basically the sum between the shallow and the deep component. And that then gives you the total subsidence rate at the land surface. If we then combine that with the geocentric sea level rise that is happening independent of vertical land motion, we basically get the total relative sea level rise rate that is observed at the land surface. And that then is something you can compare directly with vertical accretion data to determine whether your wetland is keeping up or not. So before we get into that, given that even a number of years ago, the amount of data from the CRIM system was so massive that we were able to do some interesting methodological analyses. And one thing Krista looked at was the question of how long of a record do you really need to have reasonably robust results. So these are examples, both surface elevation change, the upper panels here, and vertical accretion, the lower panels, that extend for almost 10 years. And the one thing you can see is, and we kind of deliberately picked examples that in this case are really well behaved. So, it's all pretty straightforward. Here we have a case where it's a little messier, and, people who've worked with these data know that these data tend to be quite messy. And what that means is that you need at least a certain number of years of observation to get robust results. And to kind of illustrate that, this is similar to what we saw on the previous slide. So this would be the long-term trend. This is a simple linear regression from surface elevation change data after almost 10 years of observation. If you would have shorter records, you would get sometimes very different results, right? Initially, you would have a very rapid decline here, but then after a few years, it would revert to actually surface elevation gain because of these higher plotting data points here. But eventually, it's going to drop down again. And you can see here that over time, the longer the record becomes, the more, as you would expect, the result will kind of stabilize at a certain value. So we did this analysis for a number of sites that had these long records. And what you see is that what's shown in the blue dashed line is, the eventual value after 10 years of measurements. And, this is an interesting example, right? Here you can see that after about 3 years, you kind of reach a reasonable number. In this case, it takes more like 5 years. In this case, it takes even a little bit longer, right? So it's not going to be the same everywhere. But based on this analysis, we came to the conclusion that you really need at least about 5 years of data to have reasonably robust results. So that basically guided the subsequent analysis that was entirely based on sites that had at least 5 years of data. And without going into any further details, I'm jumping straight to the end result here, where we're looking at the rate of relative sea level rise, so that's the sum of this shallow subsidence from our set marker horizons, the deep subsidence from GPS, and then the geocentric sea level rise. And in this case, that gives us an average value of 12 plus or minus 8 millimeters per year for this region. But you can see that there is a lot of variation, and you can see that very well here. Here as well in these cumulative frequency distributions. So one thing that is worth pointing out is this little asterisk here, and that refers to satellite altimetry. At the time of this study, which is, of course, a number of years ago, we actually had very, very limited data on geocentric sea level rise in the Gulf of Mexico. So we ended up using a number from one published study that was actually very low. And we kind of knew that it was probably lower than something that would perhaps be more realistic. But it was really all that we had at the time. And so that was clearly a limitation. And this is something that we have now been able to improve on a lot. So this is actually that opening slide. This shows one of those crimp sites. And what you see here is these boardwalks is actually where the SET measurements are done. The marker horizons are kind of in the marsh around these boardwalks. But the other thing to point out here is what's sitting here in this open water, and that is a water level gauge. And one of the really appealing things of this CRIMS program is that nearly all these CRIMS sites have a water level gauge that monitors water level change at, really at the local level, and they're usually located very close to the other instruments. And that, of course, gives us an opportunity to do something much more sophisticated. So this is a little bit of a very brief illustration from Guangdong's work that is currently in review. And what you see here is a schematic that shows our wetland deposits here, our Holocene, sitting on, in this case, a non-compressible Pleistocene substrate that in some cases is near the surface and then elsewhere dips to, more than tens of meters deep. The implications of that are quite important, and I won't have time to go into all the details here, but the SETs are in many cases anchored in the Pleistocene, but not always, as you see here. The water level gauges, they are sitting on poles that are much shallower, and they're usually something like 3-4 meters deep. So in most cases, they're literally sitting in this very compressible Holocene succession. So in order to tie those things together, you actually have to accommodate or address that difference in foundation. Again, I'm happy to answer questions about how that was done, but that's a little bit beyond the scope, perhaps, of this relatively short talk. So the really important thing to highlight here is how we were able to address sea level. And this is where we benefited tremendously from a very important study that came out just over a year ago by the French group, Cazenave et al., that perhaps for the first time demonstrated how geocentric sea level change can be monitored in the very, very near coastal zone, something that has kind of eluded the sea level community in the past. And basically, their paper includes hundreds of what they call virtual coastal stations. And 4 of those happen to be located here around, basically along the coast of Louisiana. So these are the 4 that Guangdong has used. And he was able to compare the average record from these 4 virtual stations with the Grand Isle tide gauge, which is located here, which had been corrected for vertical land motion. And the result is what you see here. And this result is really quite remarkable because we see that not only that the long-term trend is about the same, but you can see a lot of the finer details are also very similar between Grand Isle and those coastal virtual stations. So that gives us a lot of confidence in this part of the story, basically the climate-driven sea level signal. And the one thing that is, of course, important to point out that during this time, starting around 2009, the rate of geocentric sea level rise in this area has been tremendously high, right? More than 10 millimeters per year. So about 3 times the global average. So, and just to emphasize, this is independent of subsidence, right? So there's no vertical land motion in this record. So that was kind of the motivation for this study. So the first thing Guangdong did was to find out how what we see right offshore here, how that translates into the wetlands. And this is, of course, already a big step forward from, comparing a tide gauge record, that is right on the coast with wetland change that may occur much further inland. And the assumption you then have to make is that, those water level changes are going to be the same. But of course, they're not necessarily the same. And we can see that here. These are the rates of water level change or relative water level rise at all these CRIM sites. And there is quite a lot of variability, right? And generally, these rates are quite a bit higher than what we see on the coast. And the reason for that is that here, vertical land motion is part of the story. So the second panel here shows the correlation coefficient between the Grand Isle tide gauge and what we see on these water level gauges. And you see that they actually correlate pretty strongly, especially here in the Mississippi Delta, right? When we go to Southwest Louisiana, the Chenier Plain, we see very poor correlation. This is not necessarily a surprise because we know that many of these areas are hydrologically kind of isolated from the open coast. So there are some real differences here. But by and large, the correlation is quite high. So basically, the next step of this analysis was to compare surface elevation change at all these CRIM sites with local relative water level rise. And what you see here are just examples of individual records. So blue shows the relative water level rise at that site. And in brown, you see the long-term trend of surface elevation change. And as you might expect, there is quite some variation, right? We have what we call unsafe sites that all follow different forms of what we call give up. In some cases, drowning has already happened. Other sites are in the process of drowning. And then there are sites that, with current trends, we expect to drown in the future. On the other hand, we have what we call keep up, catch up, or speed up. These are different varieties where in keep up mode, they're basically the rates between the water levels and the surface elevation change are fairly similar. And here we have cases where actually surface elevation change rates are higher than the rates of water level rise. Now, I can tell you right now, these conditions are rare. And we will see that on this map that shows basically that everything in blue or bluish colors is what we call give up. And everything in green, orange, or yellow is in one of those categories that we would consider safe. So some interesting patterns here. You can see that most of these safe sites are very close to the coast. That may have to do with sufficient sediment coming in from perhaps some storms. But the vast majority is in a significant deficit. So the important point here is that this is a really big step forward in how we can analyze these data, because we can now actually look at what is really happening at the site level, not only in terms of surface elevation change, but also in terms of local water level change. So to kind of wrap up with my key takeaways, the first one is, of course, that uh, kind of methods finding from a number of years ago, where we showed that you really want to have records that are at least about 5 years long. Otherwise, you may simply have too much scatter to produce reliable trends. Um, the second point is that, even though that method of comparing RSET data with tide gauge records, um, of course, it's it's a useful first step, but we have to be aware of the limitations, and uh, we have to try whenever we can to move towards something different. And now we have this huge benefit of coastal satellite altimetry, which is becoming increasingly available. Uh, the expectation is that that will only get better in the future. We have this new SWAT mission that was just launched last year that will probably produce a lot more near coastal sea level data that can be used for these types of purposes. And finally, these water level gauges that are part of the CRIMS program, um, I won't say that they're necessarily incredibly cheap. I honestly don't even know exactly what the costs are. But this is not incredibly outlandishly uh, expensive equipment. So having even a more limited amount of that kind of data available is going to be really, really beneficial to allow for a more direct comparison with RSET data. So with that, I'm at the end of this presentation, and I'm going to be happy to answer questions during the upcoming session. Thank you.